From the Biological Psychiatry family of journals, this is the Biological Psychiatry Podcast, where we discuss the latest research on psychiatric disorders and their treatments. Thank you for joining us. I'm your host and social media editor, Elvisha Dhamala. When we think about how trauma affects the brain, we usually think about the regions involved in fear, memory, and emotional regulation. But what about the parts of the brain that simply help us see? It turns out the visual cortex, the region that processes what our eyes see, may be affected by trauma in ways we're just beginning to understand. A new study takes a closer look at this question by comparing the brain structure of people who recently experienced a traumatic injury with people who didn't. What they found was interesting. The primary visual cortex was thicker in those who had recently experienced trauma, but the thicker visual cortex did not seem to be related to PTSD symptoms. This suggests that trauma itself, rather than post-traumatic stress disorder, may have an impact on visual processing. Joining me to discuss this is Dr. Nathaniel Harnett from McLean Hospital and Harvard Medical School, first and corresponding author of a recent paper in Biological Psychiatry, Cognitive Neuroscience and Neuroimaging. Dr. Harnett, welcome to the Biological Psychiatry Podcast.
Thank you.
To start things off, what do we know about how PTSD affects brain structure, and why is the visual cortex in particular an area of interest?
It's a really good question. So, we have been looking at the neural correlates of PTSD for the better part of almost 3 decades now. And we've learned a lot in terms of how, chronic PTSD is associated with brain structure, brain function, all these different aspects of neurobiology. One of the things that we see pretty often are changes in what we typically consider threat neurocircuitry. So this is regions like the prefrontal cortex, hippocampus, and amygdala, regions that are really involved in emotional processing, threat learning, and threat responses. And what we often see across the prefrontal and hippocampal regions are these reductions in gray matter volume, in cortical thickness, that we think is related to the emotional deficits that we see in PTSD. One of the things that my lab and many other labs now across the country have been looking at is how do we use brain structure to predict who's going to go on to develop PTSD? So shortly after someone experiences a trauma, how can we image the brain? What regions come out as most predictive for if they go on to develop the disorder? And something that we've seen across several data sets now is that this structural organization really of the visual cortex, what I tend to lean towards looks a lot like the ventral visual stream, seems to be uniquely predictive of PTSD. So in recent trauma survivors and a couple different data sets, we've shown that there are these positive associations between this thickening volume sort of covariance in PTSD symptoms. And then later on, as we look at chronic individuals with PTSD, we see this sort of flip in this association, really suggesting that something is happening with visual cortex that might be really related to intrusion symptoms or the development of negative alterations in cognition and mood. Perhaps this flip from acute to chronic might be related to changes in how these symptoms express over time.
So, as you mentioned, PTSD research often focuses on the threat neurocircuitry, including the regions that you described, like the amygdala, hippocampus. But here you were talking more about sensory processing. Can you give us an overview of what that circuit looks like and why it might matter?
When we think about how the brain is processing information in PTSD, we think about it, as you just mentioned, in terms of that threat neurocircuit, but we often think about it in terms of, people are just learning incorrect associations, right? Like there was something dangerous, and now that's being attributed to something that's safe. But there's this sort of implicit assumption that information that gets to these threat neurocircuits has already sort of valence neutral, right? Like it doesn't really have any effective properties. And I don't think that's entirely true. The way in which visual stimuli gets into these different brain regions through a couple different pathways. The one that we focus really on goes from the retina through lateral geniculate nuclei, and then through hierarchical processing through these early visual regions, visual areas 1 through 4, that then move on through the ventral visual stream, this sort of canonical what pathway, this object recognition pathway. And what might be happening, what we think about in my lab and a couple other groups now are starting to think about is it that there is information that, as it is hierarchically processed, something is happening, some dysfunction of how that stimulus is appreciated as it moves through this stream might be then making its way to these quote unquote higher order threat involved brain regions. And that is sort of compounding the emotional difficulties that you might expect. And so we really think about these sensorial circuits as being important, not just for, okay, can you see the thing in front of you, but how are you actually processing and working with these other higher order brain regions to understand the meaning of what you're looking at?
So essentially, these sensory areas need to take in that information of the stimuli before it can then get passed on to the threat neurocircuit and have a downstream effect. Is that correct?
That's such a much more succinct way of what I said. Thank you. Yeah.
A central goal of this study is to distinguish brain changes related to trauma itself from those that are tied to PTSD symptoms. Why is that distinction in particular important, and what are the implications of that distinction?
PTSD is a very unique psychiatric disorder because it is one of the few disorders in which we know what the cause is. Definitionally, for someone to be diagnosed with PTSD, they have to have experienced trauma. And that offers us a really unique opportunity to time lock when their symptoms simply must start. And so, if we can look at what's happening in the brain as close to trauma as possible, we want to develop biomarkers that help us understand who's susceptible, who's going to go on to develop the disorder, but also biomarkers of treatment, who's going to be most responsive and most receptive to different types of interventions so that we can prevent the development of the disorder. The problem that we run into, though, is that if you only look at associations between what the brain looks like soon after trauma and PTSD symptoms 2 weeks, 6 months, 12 months after the event, you're really only understanding if there are these sort of associations, right? Like things that might be sort of predictive. What you might be missing, though, are sort of unique adaptive potentially responses or even maladaptive responses that are due to the trauma itself. And if you want to have biomarkers that are going to be really functional, they're going to actually predict what you want to predict, you need to be able to differentiate between, is this an impact of trauma, in which case it could lead to PTSD or it could not lead to PTSD, depending on individual variability in susceptibility or resilience? Or is this really a biomarker of the psychiatric disorder that you care about?
So you mentioned the visual areas V1 through V4. For listeners who aren't familiar with the anatomy and that visual processing pathway, can you tell us what the regions do and how they work together?
The visual cortex has long been a study in imaging research. It's a long study in neurophysiology research because so much of what we do every single day involves taking in visual information. And so there's a lot of work that's been done on trying to understand very specific things that these regions do. In a very broad sense, information that hits our retina that passes through the lateral geniculate nucleus to get to the visual cortex is first processed in V1 and it builds hierarchically. So V1 is processing very, very basic stimulus information like lines or edges or spatial orientation. V2 builds on this to help discern boundaries of different stimuli, to help understand contours of those stimuli. V3 can build on that further to understand a little bit more about what objects you might be looking at and whether or not they're moving. And then V4 builds even further to understand sort of more complex geometric features. And then all of that information is then spread, if we're thinking about the ventral visual stream as opposed to the dorsal visual stream, to the inferior temporal gyrus, to V5, to MT, to other regions that, again, subsequently build. One thing that's very interesting about these circuitry, or about this circuit in particular, is that a lot of times we think about them as like it just builds in one direction, but it's actually a recurrent processing and feedback loop. And so information that passes from V1 to V2 and V3 and so on actually can go back for certain regions. And so you can have this very interesting relationship between regions where, yes, they're feeding information forward, but they're also feeding information backward. And you think about that in regards to, say, the threat neurocircuit, where information has this sort of affective or emotional valence to it, this emotional tone. How then might that sort of feed backward into these other regions? And does that impact the way in which you process these sort of visual information? So, getting back to your earlier question, understanding how these regions in particular might be important for PTSD and trauma has been really important for us.
talk about your study design. You have a discovery sample and a replication sample, and they differ in important ways. So they have different demographics, different scanners, different clinical assessments, and even slightly different control groups. Why use two different samples to begin with, and how does this actually strengthen your findings?
So the first reason to use two different samples is it's always nice to be able to show that you can replicate an effect. When we initially started doing this research in the discovery sample, we said we thought that we were going to see some difference in visual cortex thickness that was related to trauma and probably related to PTSD too. And we did see something related to PTSD, but the thing that came out strongest was this difference in cortical thickness between individuals who've been recently exposed to a traumatic event and individuals who had not recently been exposed to a traumatic event. It's about 30-day window in V1, where these recently trauma-exposed individuals showed greater thickness in visual area 1, which I think that sort of as a heuristic is sort of hard to wrap your head around at first, if only because a lot of the way in which we treat brain thickness or brain volume is that is a measure of brain health. So more thickness or more volume, that's better. And stress is bad, so it should lead to less brain health. So why is it that individuals who just experienced something really stressful, really traumatic, might actually show what we want to infer is greater brain health, but really let's think about it as just cortical thickness. And so that is already sort of an uphill battle in terms of like, well, did we do something wrong? Is our sample just idiosyncratic, esoteric in some way? And very luckily, we knew of a data set that had some of this very similar data, had a very similar design from my original dissertation mentor at the University of Alabama at Birmingham, Dave Knight, and his collaborator, Amory Knight. And so we thought, if we found this here, we should at least test it and see if we find it again. But like, it was really important to us to say, like, is this real or did we do something wrong? And so when we found it in the replication data set, that was really sort of a moment for us to say, okay, we think this is a real thing, that there's something biologically happening right in area V1 that has to do with trauma exposure. Doesn't seem to be related to PTSD, but it's at least related to trauma exposure. And so let's try to figure out what that might be.
What does this greater thickness actually mean biologically, and what are the potential mechanisms that might be driving that increase in thickness?
I think that's a great question. And the response to it is my favorite answer, which is I don't fully know. So there are a couple of caveats to why we could or couldn't know. But one of the things that we thought about was that maybe, just maybe, trauma exposure would be associated with not sort of neuronal atrophy, but maybe some sort of aspect of neurogenesis. Is it that right after trauma exposure, individuals have this like proliferation of neurons within a month? That doesn't sound very plausible, but we thought that might be an idea. So we actually, in addition to looking at cortical thickness, also looked at cortical volume. These are sort of distinct metrics in how they're calculated. Thickness looks at the distance between the white matter and the peel boundary. Volume looks at sort of the amount of gray matter itself within an individual's voxels. And we might use that as a proxy, and other sort of prior animal research has shown this is a good correlation for the amount of neuronal bodies. When we looked at gray matter volume in these samples, in both the discovery and replication sample, we didn't see any differences between recent trauma and non-recent trauma individuals. And so that really suggests that it might not be really sort of neural changes. It might be something else. And so maybe there is sort of neuroimmune responses, neuroinflammatory responses as a result of experiencing that traumatic event. And that's leading to some sort of like microedema, like a little bit of fluid building up because of that immune response. That is sort of the end of where we came. But biologically, I think we're leaning towards, at least for this acute phase after the traumatic event, maybe there's some sort of immune response that's driving this increased thickness. And maybe you might expect it to, among individuals who don't develop PTSD, to go down over time.
You mentioned this change in V1 thickness that you observed was related to trauma exposure, but not symptom severity overall for PTSD. What exactly does that tell us in terms of the acute versus chronic effect trauma on these brain regions?
We can glean quite a bit, I think, about the acute effects, right? Because all of this imaging data, at least for our recent trauma-exposed individuals across both samples, was collected within about 30 days after the traumatic event. So at least acutely, we're pretty confident in inferring that trauma I want to be careful about my wording here, may lead to an increase in cortical thickness, at least in the short term. One of the interesting differences between the discovery and replication sample data set is that the discovery sample, our non-recent trauma survivors were just non-recent trauma, and the replication sample, they were non-trauma exposed. And so the fact that we don't see differences in both groups or in both data sets really suggests that over time, this sort of difference in V1 thickness may dissipate. And again, might not be related to PTSD. This might just be sort of the body's natural response for whatever reason to experiencing an acutely traumatic event. It's difficult to know without subsequent imaging data. Like if we had imaged people both at that sort of initial 1 month, 3 months, 6 months, maybe 12 months, maybe one day we can get the funding to do that sort of study. It'd be a lot easier, I think, to know like, okay, is there what is the sort of time course of that thickness, and does it really subside over time? And part of the reason I'm trying to be careful is I had it drilled into me very early on that it's a bit of a faux pas to say change when you're doing a cross-sectional study. These are all individuals collected after the traumatic event. And so we don't really know what their brains look like right before. Although I think, I lean towards that it's probably change.
So, in contrast to what you saw with V1 thickness, V4 thickness was negatively associated with PTSD symptoms, but only in the discovery sample. So, what might V4's role overall in visual processing have to do with that? And why might those results not have replicated?
Yeah, it's a good question. I think that in comparison maybe to the V1 findings, the ventral V4 findings fit a little bit more of our heuristic that stress would be associated with that sort of aspect of lower brain health, right? If we wanted to really simplify it. And if we're going to do, I think, a little bit of reverse inference, we really know that V4 is very involved in object recognition, especially for complex geometric shapes and things like that. That it's really involved in, selective feature extraction. And one of the things that we think about in PTSD is this sort of overgeneralization of acquired threat to new safe threat. So this idea that when you learn that a cue predicts an aversive outcome, you start to generalize that association to other cues that don't necessarily predict that aversive outcome because you're trying to maintain the sense of safety. And part of what we might think is that maybe there is the disruption in this brain region that's really important for recognizing what exactly it is we're looking at and for having that understanding of the complex shapes that can help differentiate these objects. And maybe that helps contribute to fear overgeneralization in some way, right? There's sort of this inability in some cases or perhaps to really differentiate between these different objects, at least at like a very basic neural level, maybe not at a conscious level. One thing though that you brought up is that we didn't see this in both data sets. We really only saw this in the discovery data set. And it's really unclear to us if that is a function of the type of measure we used or the type of sample that we included. The discovery sample, I think, had greater PTSD symptom severity overall compared to the replication sample. But it's unclear, again, if that's because in one we used a PCL and in one we used a PDS, right? Different ways of measuring these PTSD symptoms. And so the jury, I think, is still out in terms of whether or not that is going to be a generalizable finding, but that's sort of where we're sort of landing with what we might hypothesize is going on.
Another interesting thing you found is that the trauma related thickness differences were specific to the visual cortex. So you didn't see them in terms of global cortical thickness or in other regions like the prefrontal cortex. What does that tell us?
Yeah, the fact that we only saw these findings in visual cortex and it was robust to a number of different covariates, including just using global or average cortical thickness, in some ways was a nice confirmation that this is sort of V1 specific, and other ways adds to our confusion about what these sort of threat neurocircuit regions that other large scale analyses have shown in PTSD might be doing, or if the thickness and volume and just general neural structure differences might be something that build up over time, right? So we can imagine that what may happen, one sort of speculative hypothesis, is that for individuals that are susceptible to PTSD, that show this sort of what I'll affectionately use as change in V4 thickness, that leads to subsequent alterations and processing of stimuli, exacerbates PTSD symptoms, and that chronic stress of then having those symptoms, having that disorder, then contributes to greater atrophy in these threat neurocircuit regions, right? So it's a question of, which brain region is sort of impacted by trauma versus which are sort of impacted by the experience of PTSD itself. I think what this tells us is that something else has to be happening for these threat neurocircuit regions that we know are important for PTSD. And maybe it is simply just the case that as time goes on, as these individuals live with this stress, that's when we start to see what we might call breakdowns in the underlying structure of those regions.
So your control group in the discovery sample included people with prior trauma histories, but no recent trauma. And V1 was still thicker in the recently exposed group. Does that suggest that the changes that you see or the differences that you see are transient, where thickness actually increases acutely after trauma and then might normalize over time?
Yeah, I think that's exactly where we end up in our inference, right? That based on the study design, based on what we have, based on when our imaging was done, we really think these are sort of acute changes. Again, it's hard to know without the longitudinal data if, among some individuals, it stays elevated over time. Among maybe for those that are most susceptible to PTSD, it drops more precipitously back, below baseline. But I think you're exactly where we are in that these V1 trauma-related changes we think are most likely transient. They probably have some other sort of importance that we just weren't able to glean here. Again, maybe it's this neuroimmune thing. Maybe it is how this brain region is talking to other brain regions. It's really hard to tell with just the structural data. But we think that thickness is probably going to be transient. It's just something else that we didn't get that might be related to the psychiatric disorder itself.
In the paper, you acknowledge several limitations, including small sample sizes and, as you mentioned earlier, the absence of pre-trauma imaging. What does that shape how and what we can and can't conclude from this study?
So based on my behavioral neuroscience training, what I would say is we can conclude exactly what we put in the title of the paper, that thickness is associated with differences in V1 thickness. What our design allows us to say is that trauma seems to be associated with V1 thickness independent of PTSD symptoms, and ventral V4 thickness seems to be associated with PTSD symptoms, which may or may not be independent of trauma, given definitionally how we define PTSD. I think that our limitations are really that in an ideal world, we would be able not just to look at individuals who recently experienced a traumatic event, but people before they experienced trauma to know what their individual profiles of susceptibility to the disorder would be. And without that pre-trauma baseline, even in the case where we have a discovery and replication data set and we think it has to be related to change, it's really hard to know for certain, as much as we need to be, what those brain profiles would look like and whether or not trauma is inducing this change, or if the fact that they're experiencing trauma might be hiding some other pre-traumatic association with PTSD. You can imagine that V1 thickness among individuals who have not been exposed to trauma and are about to be might be different in some way. Maybe there's some brain thing that leads people to be exposed to trauma. I don't necessarily think that, but as scientists, we have to be open to alternative explanations until we have evidence that disproves that. So it would just be nice to have some sort of pre-brain imaging to be able to devise new biomarkers, really.
Would you say that there might be something in the pre-trauma imaging that could indicate susceptibility to PTSD?
I think that is a lot of people's hope. I think that a number of us really want something that helps us understand, if the worst were to come to pass, right? If the worst happens, can we get individuals help even sooner? And ideally, having that pre-trauma profile, that pre-trauma neural signature would say, okay, Now they don't need to get brain imaging right after they've fallen and broken their leg or right after they've been in a 12-car pileup. We can just immediately know that they need the most amount of treatment or they need this specific treatment. And then from a basic science standpoint, it would just be nice to know if is this really a change as a function of trauma, or is this just something that, is a spontaneous recording that might not be related?
My last question is, if there's one key message you'd want clinicians, researchers, and the broader public to take away from your work, what would it be?
Key message that I'd want everyone to take away is that the things that happen to us are embedded in us. That some things that we experience have to go someplace. And what I really think, despite the limitations, is that what we've shown is trauma has some very acute impacts on the brain. It's associated with PTSD through visual neurobiology. And as much time as we've spent on prefrontal cortex, hippocampus, and amygdala, because they are our favorite brain regions, I think if we want to tackle the issue of susceptibility, we really need to zoom out and expand the circuits that we're looking at so we can devise the best types of biomarkers to help those who are going to be most in need.
That's all for today's episode. Thank you to Dr. Harnett for joining us to share his work on trauma and visual cortex structure. For our listeners, you can find the full paper in Biological Psychiatry, Cognitive Neuroscience and Neuroimaging, and we'll include the link in our episode description. To learn more about our journals, please visit biologicalpsychiatryjournal.com. You can find the Biological Psychiatry Podcast wherever you get your podcasts. Subscribe now so you don't miss our next episode, and follow us on our social media channels for highlights and updates. Thanks for listening. This podcast is for informational purposes only and does not constitute medical or professional advice. The views expressed are those of the participants and do not necessarily reflect those of the Society of Biological Psychiatry, its family of journals, or its editors. All rights reserved, including those for text and data mining or use in AI systems.